All right, this is the sixth of those life cycle cost analysis micro lessons that we're going to talk about. And we're going to jump into the annual worth giving, the present worth given an annual worth. What the idea here is that we've got some annual costs that are incurred. What might they might be energy. For example, you're going to pay a utility bill or maybe a water bill or something like that. Or you might have maintenance that occurs throughout the year. Or you might have some operational costs like running a steam plant or something like that. And those costs will occur every single year. And the way that we model this, we understand that there's minor fluctuations, but generally we consider them to be equal from year to year to year. And you can get these costs out of your WEMS data, or you can get them out of your TRIREGA data or something like that, or maybe you got a service contract or something of that nature. But these costs are going to be the same from year to year. How do we call these things in a present worth value? What is the total cost of those in a present worth value? So here's an example. Let's say you're at the higher headquarters and you're trying to put in an elevator. Now there's a couple options for an elevator. You've got what's called a hydraulic elevator, which is a great big piston that's pushing it up a floor. And it's a typical type of elevator you'll find in smaller buildings, buildings that are like a couple of stories. The problem with the hydraulic, it's a great elevator, by the way. It's a good elevator. But the problem with the hydraulic elevator is it's slow. You push the button and then ding, your next floor, that kind of thing. So it's a slow elevator. Now, on the other hand, if you go into those high-rise buildings, like if you've ever been to the Empire State Building or one of those buildings where you shoot up to the very top, they have a traction elevator, which is an electric motor elevator. And those things can be much faster. However, they have a lot of maintenance costs. These are the ones that are breaking down all the time. And those elevators will cost you more in maintenance. So let's say that we're at our higher headquarters and we're thinking through this, and one of the things we want to see is what is the cost, what's the present value of those costs. And so we've got these maintenance costs, which are one of the issues, one of the life cycle costs we need to consider. So how do we take that additional maintenance cost and call it a net present value so we can add it up to all these other costs and consider which is the best option? So this is, in our 4 different formulas, this is the second of those 4 different formulas, P given A. That's the way we kind of term the present value given the annual value. In fact, you might even see P/A, which is a annotation. It doesn't mean a division problem. It means that you get P given A. And again, we're going to use the interest rates we're using for the course. So you've got this formula. It's the same variables we had before. So we didn't change the variables. We've got the interest rate we need to know. We need to know the number of years. And in this case, this is the total number of years of the effort because we're going to presume the annual cost occurs throughout this entire term. So the entire term of analysis. And then you've got the annual value that's coming in. What's the annual cost? So let me give you an example. What's the present worth of 10 years of maintenance on a chiller? So we've got a chiller that we're going to install or something. Maybe we're considering a certain type of chiller, and there's a number of costs that go along with it. But one of the things we're looking at is the annual maintenance. And let's say we've looked in our maintenance records and we identify that we would spend typically about $500 a year. Now those $500 might occur throughout the year. They're going to occur like maybe they're going to occur quarterly. Or maybe they occur every week. Or maybe they just occur once. We do it once a year. Whatever it is, but we're going to presume that we count the cost at the end of the year. That's just an industry standard. It's what makes these formulas work. So we're going to presume that they occur at the end of the year. So this $500 we're all going to accrue at the end of the year. Now we're going to say it's 10 years that this chiller will last. And so that gives us a 10-year interest rate. We saw on our table before, that's 1% or 0.01. So we've got that great big formula there. Now I know that looks like a great big formula, but if you've got it built in a spreadsheet or if you know how to work from the inside of the parentheses out, check out our micro video on order of operations. But if you know how to work that out, then basically you can just chug through this thing. So let's see what we've got here. 1 plus I to the n. 1 plus 0.01 is 1.01 to the 10th power. And then we subtract 1 from that. All right, that's on the top. On the bottom, we got I, 0.01, times that 1.01 to the 10th power. So the same thing we did here, we got the same number there. Multiply those two guys together, divide the top by the bottom, and you come up in this case of 9.4713. And so we take that $500 value times 9.4713, and we come up with $4,735.65. Now, somebody might be inclined to say $500 a year for 10 years, let's see, that's $5,000, Tom. Well, it's not exactly $5,000. And when you got a lot of different cash flows, by overemphasizing those future investments and calling it $5,000, you will actually justify investments that don't necessarily have the same amount of return on them. So that's why we go through this analysis. $4,730, that's close to $5,000 because it's a shorter term. It's only 10 years. We're not looking at something that's got 25, 30 years. But that's close to $5,000, but it's not $5,000. And when you add all these things up, those little bitty differences, that's not it's even little bitty, but those little differences make a big difference. Now, somebody might be saying, wait a minute, Tom, that last year, are you really going to maintain this thing? What if we know that we're going to do it on a quarterly basis? You're not going to do that last quarter of maintenance on it, right? You're going to replace it. It's going to break down. You're going to get rid of it. Why would you consider that last little bit of maintenance? What if it's a weekly? Would you do that last week? Would you do that last semi-annual? Whatever it is. And the answer is maybe not, but we're going to count it anyway. See, the idea is we don't necessarily know in an annual situation exactly how that annual cost is going to incur. It might occur weekly. It might occur periodically whenever we can schedule it. If it's occurring early in the year, we're going to do it. If it's occurring every couple of weeks, we're going to do it right up until the very end. And so, on an annual basis, the convention is you include the last year full. And that's a simplification that makes this formula work. So for, again, annual, we are going to include everything all the way to the very last year. Now, if it's a future cost, let's say we're going to repair this thing in year 5, and then we're going to repair this thing in every 5 years. Well, then you wouldn't do it in year 10, right? Got it. I got that part. So for a P given F, remember, not a division problem, this is just the annotation, how we write it. A P given F situation, we don't consider the last year. But if it's a P given A situation, you do count it. So the important thing to remember, and this will occur in your homework, somebody's going to come back and say, well, I didn't count the last maintenance. Well, I only did it for 9 years instead of 10 years or something like that. You count it all the way through to the end. And another reason I want you to think about this, let's say this occurs once a quarter. Well, what that would mean is I'd have to do all 10 years, and then I have to take away 1 quarter's worth at the very end. So I've got a P given F situation there that I got to take it away. Well, let's say it occurs semi-annually. Well, I got to do all 10 years and then take away 1/2 of a year's worth at the end. Really, I'm complexifying the problem. I'm giving you more equations at that point. And goodness gracious, we don't need more equations. This is an approximation process to be able to enable us to make decisions, and it should be a quick process. So the convention, again, you count all the way through. Let's take a look at a second example. We're going to take a look at steam traps, a mechanical example. What we have on the base is some steam traps. And you had an auditor come in and take a look at these things, and he's recommending that you're going to install a wireless steam trap monitoring system. Now let me explain what steam traps are so you can kind of get what the idea here is. If you've got a centralized heating system on the base where they got steam or high pressure water or whatever it is, that's going around on the base, if you've got steam, what they have to have at every single location where you pull the steam out of that central system, every single location, you've got a steam trap. And what that steam trap does is as the water cools and as the steam cools, it will have a condensate. And this steam trap collects that condensate at the location and sends it back to the steam plant. Now, what happens with steam traps is they leak. So they will develop a leak, and then what that is essentially, I want you to imagine turning on the hot water faucet at your house. Now, you may not be turning it on full, but you're turning it on, and you're letting it run for weeks and weeks and weeks. Can you imagine the cost to you for doing that, both in the water and in the cost of the energy that you're putting into that, putting down the drain? Well, that's what's going on when the steam traps start leaking. So what we normally do is our shops will go around and inspect them on a periodic basis, maybe once a quarter. That's, by the way, a pretty aggressive schedule. If your shops are doing it on a quarterly basis, great on them. And that's what we're going to model behind us, that they're doing it on a quarterly basis, checking these steam traps out. But that means that anytime during that 3-month time frame, that leak might have occurred. So you've got an average, when leaks occur, they've been running for, on the average, about 6 weeks during that time period. And then you've got to schedule a team out there to get to it. So now you can see why investing in a wireless monitoring system that gives you immediate feedback when a steam leak occurs might be something that would save you some money. So what they've done is they've come back and said, yes, we think that this is a good idea. We're going to put in this wireless monitoring system, and it's going to have a 20-year life. So that's our period of analysis. So the manual inspections occur quarterly, we mentioned that, and each one costs 140 man-hours, and there's a shop rate of $70 an hour. Now, you might say, Tom, why didn't you just give me the cost? And the answer is that in the real world, they don't just automatically give you the cost. You've got to go out and find it. You've got to find out how many man-hours, and that's going to be in your maintenance records. And you got to figure out what your shop rate, and that's going over to the resources people. They'll tell you what your shop rates are, and you got to start doing some of this development yourself. So I'm kind of modeling that, okay? Now, the average inspection identifies about 16 leaks. You got hundreds of these things across the bait, maybe even thousands of these things, and you find out that there's 16 on any particular quarter that have leaked. We figured out what the cost of that is, how much steam we've lost over that 6-week time period. Remember, on an average 6 weeks, plus the average of 2 weeks to get a team out there to repair it. So we've got a lifespan of about 8 weeks per leak. We've figured out what that cost is per year. Now, how did you get this? Well, you're going to have to get some mechanical guy to go out there and check utility bills and quantities and how much the amount of steam is. So that's going to be dependent upon the location. But let's say we've determined it out to be $187,000 a year. So this wireless system would reduce both the cost and the amount of maintenance by 75%. You might say, well, why wouldn't it reduce it all the way? Well, you still got steam leaks that you got to go out and fix. These things are still going to leak. And it's going to take you about 2 weeks to get them out there. So that didn't change with an automatic system. We just figured it out quicker. But that 2 weeks is a lot better than 8 weeks. So that's 75% as far as the cost of the steam. And we're still going to have to go around and inspect these little monitoring systems. I mean, there's going to be monitoring systems that need battery changes, and you're going to need to make sure that they're still operating optimally. So let's say we did that once a year. Well, we've just reduced it from quarterly to once a year. Well, that's 75%. So we've reduced both of these things 75%. That's your savings. What is the net present value of annual savings of the wireless system? And remember, savings is the difference between the way we do it now and the way we're going to do it under this new system. So we're going to have to figure out a subtraction problem there. So we're going to draw that cash flow diagram, and it's a 20-year system, so we get 20 years out here. We've got the maintenance across this period. 140 hours of maintenance times the shop rate. That's going to be our cost. It occurs 4 times a year, and our savings are 75% of that. Remember, we do 100% of it now. We're going to do 25% of it later. The 75% is the difference. So that's our savings. So our savings are $29,400 a year. Now let's throw on that energy cost. The energy cost is at $187,000. And we'd only be losing 25% now as opposed to the 187 before. So the savings is the 75%, which is 140,000. So these two are our annual savings. So the annual savings is $169,650 each year. And remember, the good news is that these are the things, the money we're recouping, which means in our overall equation, they are negative. We consider savings and revenues to be negative. So what is the net present value of this? Well, we know our savings. We know the interest rate for 20 years. If you go back to that chart, it's going to be 1.2% or 0.012. And our number of years is 20. So we throw it into that equation. Our calculator moans and groans a little bit. And out comes a value of 17.687297. The value. Multiply times 169,000, and we come up with $3,650,000. And remember, again, those are savings. Now, remember, you might be inclined to say annual cost, 20 years, well, 20 times those annual costs. Well, no, that's not 20 times the annual cost. That's 17.6 times the annual cost, or 17.7. So it's not, that approximation isn't going to work for you in the long run. Now, that's the answer to the net present, or the present worth of those savings. Let's take this a little bit further and show you why this is important. Let's pretend we're considering this investment, and we have 500 steam traps on the base, and each wireless monitor is going to cost me $800. So I'm going to invest in putting these new wireless monitors in all my steam traps across the base, 500 of them, and each one's going to be $800, which means my total investment is 800 times 500. Let's see, math in public, I think it's $400,000. Okay, so what's the simple payback? And what's the savings investment ratio? That's taking it back to the lesson a couple of lessons ago, about lesson number 2, right? Okay, now we're on the Magic Wacom monitor. Let's take that 800 times the 500, and lo and behold, yes, I just checked it out. It is $400,000. So what's the simple payback? Well, our investment is $400,000. We'll call that P. That's the present worth of the initial investment. We know our annualized savings are $169,000. So the way that you work this is simple payback is that $400,000 divided by the annual savings, and that's going to give you this is cost per year. We cancel the units out, and that years come up on top. You come up with this, we'll have a 2.4 years simple payback. And that's good. That means you've got payback, and that means you're going to have it come up in less than 5 years. So generally, that's a good investment. Let's figure out what this savings to investment ratio is. And that is, if you recall, the investment is right here, or the savings is right there, the net present value of the savings, and the initial investment here is right here. So the savings is $3 million divided by the investment, and that gives you a 7.5. This is very good, folks. I think I've mentioned this before, but of course, above 1 means you've got a good investment and means you have savings. But a 7.5, anything above 1.5, the AFCEC folks are looking for. Especially in the energy program, they're looking to make that investment. Now, some of these savings are in maintenance, and it's got to be greater than a certain percentage for them to invest in out of the energy program. But this is very competitive for an energy program investment. So that's a great example of how we now use this to make funding decisions. So again, this is just kind of carrying this annualized formula out Why would we want to calculate that annualized formula? Not just to come up with the net present value, but it also really tells us some things as far as why we want to invest this thing. So going into this, taking this a little bit further might show you why this is important to you. So again, annual costs include both revenues and expenses, and you need to convert them to present value before you do any analysis with it. So that's what it helps to tell us. Again, once you have a spreadsheet built, that can really facilitate this. I'll emphasize yet again that you need to build your own spreadsheets. That's why I don't hand these things out as a spreadsheet, because you need to understand how this all works. You need to test it out. Try it on the sample problems, try it on the practice problems, and see if it works for you. Because I'm telling you, all you need to do is miss one parenthesis and you're going to get the wrong answers. And I'm not going to set you up for failure by generating software for you that you now need to deglitchify or whatever, make it work for you.